All right, diving right in today. We've got this paper, Flexible BERT Model, Enabling Width and Depth Dynamic Inference. And wow, it really gets into how we can make these large language models, these LLMs everyone's talking about, a bit less, well, resource hungry.
Yeah, that's the big challenge now, isn't it? I mean, as LLMs get more powerful, they just demand more and more computing power, and that makes it really hard to, actually use them in the real world,
Mhm.
especially if you're not working with like a supercomputer.
Exactly. I mean, not all of us have access to those massive server farms.
Yeah.
So this flexible BERT, it seems to offer a solution, but how? How does it manage to be more efficient without, sacrificing accuracy?
Well, the key here is they've introduced a couple of new things like neural grafting and this dynamic inference framework. It's like they've given BERT, the model, a whole set of tools and then like the smarts to know which tool to use for each job.
Okay, now you've got me really intrigued. Let's maybe start with the problem itself. We know that, like, traditional methods for making these models smaller, things like knowledge distillation, they always seem to come with this trade-off. You shrink the model, but you lose some accuracy. How does flexible BERT deal with that?
So what they've done is really interesting. They're not just trying to shrink a single model. Instead, they train flexible BERT to create a whole bunch of subnets, each with different uh, widths and depths.
So instead of one giant BERT, we've got like a whole team of smaller BERTs, each one sort of specialized for certain tasks.
Yeah, that's a great way to put it. It's like think of each layer in BERT as a network of roads. The width of those roads, that's like the number of lanes. So more lanes, more traffic can flow through. And the depth, well, that's like having multiple levels of roads, stacked on top of each other.
Okay, so if a task is pretty simple, flexible BERT can just use a subnet with fewer lanes and levels, and that saves processing power.
Exactly. And that's where that dynamic inference framework comes in. It's like having a really smart traffic controller that analyzes the text coming in and then directs it to the right subnet for the job.
Makes sense. It's all about using the right tool, right?
Yeah.
But this neural grafting thing, it sounds a bit, well, a bit intimidating, like some sort of Frankensteinish experiment.
Yeah, the name's definitely catchy, but the idea is actually pretty elegant. What neural grafting does is it tries to make those smaller subnets perform better by sort of reactivating parts of the model that weren't really being used before.
Reactivating. You mean there are, like, parts of BERT that are just sitting there doing nothing?
You could say that. Even in these huge LLMs, not all parts are equally important for every task. So they took inspiration from this idea in biology, nerve grafting. It was like when you connect a healthy nerve to a damaged one to regenerate. They're doing something similar here, taking the activation signals from the most important modules and using those to kind of wake up the less important ones.
Ah, so they're giving those sleepy parts of the model a jolt of energy and getting them to contribute more.
Exactly. And there are a couple of ways they do this. Internal grafting and external grafting.
Okay, I think you need to unpack that a bit.
Yeah.
What's the difference between internal and external neural grafting?
So with internal grafting, they're focusing on optimizing the flow of information within a single layer. It's like they're prioritizing the connections from the most important to the least important submodules within that layer.
So it's about rewiring the connections inside a single layer to make the information flow more efficiently. What about external grafting then? Is that like bringing in information from outside the model entirely?
You're on the right track. External grafting is about leveraging information from other BERT models that have been trained kind of separately. It's like having a team of experts, each one specializing in something different, and then letting them share their insights to improve, the overall performance.
Fascinating. So flexible BERT can work solo or it can collaborate. But before we dig deeper into how this whole dynamic inference framework works, I think we need to step back a bit and talk about the training process. I mean, training a whole family of BERTs can't be easy.
You're right. It's definitely computationally intensive. They use this technique called knowledge distillation, KD for short, to kind of guide the training.
KD, isn't that like the mentor-student approach, where a smaller model learns from a bigger, more experienced one?
Exactly. The original BERT model acts as the teacher, and all these different subnets are the students. And during training, those subnets, they don't just learn from the data, they also learn from the predictions and internal representations of that teacher model. So it's like double the learning.
So they're getting guidance from the data and from the master BERT. That's really clever. But how does it actually, work in practice?
Well, they have a pretty structured way of doing it. They start by training what they call with adaptive subnets.
So they're varying the number of lanes first while keeping the number of levels the same.
Exactly. These width-adaptive subnets have different numbers of attention heads and neurons in those feed-forward networks, but they all have the same number of layers as the original BERT. And they're trained, with the data and the knowledge from that master model.
Got it. They find the best width for each subnet, and then they move on to the depth.
Yeah, that's the idea. So once they have a good set of those with adaptive subnets, then they move on to training what they call depth adaptive subnets.
So now they start changing the number of levels for each of those with adaptive subnets.
Right. And by the end, they end up with this whole family of flexible BERT models, each one, tailored for a different level of complexity. It's like having a BERT for every occasion.
That is seriously impressive. But how do they actually know how much brain power each one is using? I mean, how do they measure the computational complexity of flexible BERT during inference?
Well, for that, they use a metric called FLOPs, which stands for floating point operations. Basically, it's a way to count how many computations the model needs to do for a given task. The fewer FLOPs, the more efficient it is.
Oh, I see. It's like counting the number of steps it takes to get to the answer. Fewer steps, faster, and more efficient. But before we go on to how this dynamic inference actually works, I'd love to get a better picture of what each BERT layer is actually made up of. What are the building blocks, so to speak?
So each BERT layer has a few key parts. First, you've got the attention mechanism. That's how the model focuses on the most important parts of the text. And then there are the feed-forward networks. Those process the information and pull out the meaningful features. And these networks are made up of neurons.
Okay, so the attention mechanism is like a spotlight, highlighting the important bits, and the feed-forward networks are doing the real thinking, analyzing what the spotlight's showing them.
Yeah, that's a great way to think about it. And it's the width of those networks, how many neurons they have, that lets flexible BERT adjust its computational power based on the task.
So if the text is really complex, it can use a wider network with more neurons, kind of like having more brain cells working on it.
Exactly. And that's one of the biggest advantages here. Flexible BERT can adapt in a way that those traditional BERT models just couldn't.
This is really groundbreaking stuff. It sounds like flexible BERT could be a real game changer for LLMs. But we're just getting started. I can't wait to hear more about how this dynamic inference framework actually works in practice.
So we've been talking about how flexible BERT creates all these different subnets, but the question is, how does it actually choose which one to use when it's, actually working on something?
Yeah, that's what I'm really curious about. It's like,
Sure.
how does it know which tool to grab from that toolbox we were talking about earlier?
Right. And that's where those gating modules come in. Those are the real brains behind this whole dynamic inference framework. You can think of them like intelligent traffic directors. They're constantly analyzing the text that's coming in and then deciding which subnet is the best fit.
So they're making decisions in real time, like based on what they're seeing in that specific piece of text.
Exactly. And they're looking at a lot of things, like how long the text is, how complex it is, what kind of tasks they need to do with it. Based on all that, they predict which subnet will give the best results without, using too much computing power.
Wow, it's like they have some kind of like sixth sense for what the text needs. But it can't just be random guessing, right? How do they actually make those predictions?
It's all about looking for those telltale signs in the text. Like, say you have a short, simple sentence. That might only need a small subnet, one with fewer layers and, not so much width. But if you have a long paragraph, something really dense and complicated, well, that might need a more powerful subnet to really understand it.
So it's like matching the horsepower to the size of the load. Small load, small engine, big load, you bring out the big guns.
That's a great analogy. And that's what makes flexible BERT so efficient. It's not wasting energy on, unnecessary computations. It only uses what it needs for that particular input.
That's really smart. But you mentioned width dynamic and depth dynamic inference earlier. Can you remind me what the difference is between those two?
Sure. So with dynamic inference, that means the model can change the number of attention heads and neurons in each layer depending on the text. Remember those lanes we were talking about? Well, this is like changing the number of lanes based on how much traffic there is.
So if there's not much traffic, it can narrow the road. And if there's a lot, it can widen it.
Exactly. It gives it really precise control over how much computing power it's using.
That makes sense. So what about depth dynamic? Does that mean it changes the number of layers, like on the fly?
Yeah, you got it. That's where those early exit off-ramps come in. It means the model can decide how many layers it actually needs to use. If it's pretty confident in its understanding early on, it can just skip the later layers and save some time and energy.
Like taking a shortcut when you already know where you're going. Okay, I think I'm starting to see how these gating modules are pulling all the strings here. They're like the masterminds behind all this efficiency. But the big question is, how well does it actually work?
Well, the results are really impressive. They tested flexible BERT on a bunch of different benchmarks, things like the GLUE benchmark for understanding language and the SQUAD dataset for reading comprehension.
So they really put it through its paces, and what did they find?
It consistently did better than other efficient models, like DistilBERT and TinyBERT, which are specifically designed to be, lightweight. And here's the kicker, in a lot of cases, it actually did just as well as the original BERT, even though it was using way fewer resources.
Wow, that's like winning a race while carrying a lighter backpack. So it's not just efficient, it's powerful too. Do you have any specific examples of how it achieved that?
Sure. For example, on GLUE, it got a 1.3-point improvement in the average score. And on SQUAD, it got a 2.2-point increase in the F1 score.
Mhm.
And all that while using something like 45% fewer computations than BERT-base.
Those are some serious gains. It really sounds like this could change the game for LLMs. I mean, think about it. This means we could start using these models on all sorts of devices that just don't have the power to run the full-size versions. Phones, smartwatches, maybe even those smart refrigerators everyone's talking about.
Exactly. And it's not just about bringing AI to new places. It could also make existing applications way better. Things like language translation, chatbots, even tools that can help us write and understand creative text formats.
The possibilities are really amazing. It feels like we're moving into this new era of AI where these models can be part of our everyday lives.
It's a really exciting time. And as the research keeps going, I think we're going to see even more innovative applications for flexible BERT and these other efficient models.
Can't wait. But before we get too carried away with the future, I want to dig a little deeper into how they actually visualized what was happening with this neural grafting. Did they actually look inside the model's brain to see how it was working?
They did, and the paper actually has some really cool visuals that show how it all works. For example, Figure 4 shows how the importance scores for the different attention heads changed after they applied neural grafting.
So it's like seeing a before and after picture of the model's brain activity.
Yeah, that's a good way to put it. And what they found was that neural grafting really encouraged the different parts of the model to work together more. It's like activating a whole network of pathways so the model can use more of its knowledge and processing power.
So it's not just about activating more parts. It's about making them work together better. That's pretty amazing. What about Figure 5? Did that show how neural grafting affected how the model actually understood the text?
Yeah, that's right. Figure 5 focuses on a specific example, a movie review, and shows the attention maps. What's really interesting is that it shows how neural grafting leads to more diverse attention patterns. That means that parts of the model that weren't really being used before are now actively involved in understanding the text.
That's so cool. It's like watching the model's neural pathways light up as it learns. But I have one more question. How does neural grafting actually work on a technical level? What's going on under the hood?
It all comes down to those activation signals within the model. Remember, those signals represent the flow of information between the different parts of the network.
Right, like the electrical impulses in our brains.
Exactly. So with internal grafting, they're basically rerouting those signals within a layer, making sure the connections from the most important parts to the less important parts are prioritized.
So it's like optimizing the traffic flow within that layer, making sure the right signals get to the right places. And what about external grafting? How does that bring in information from other models?
Well, that's about combining the activation signals from those different BERT models that were trained independently. It's like taking the knowledge from a bunch of different brains and merging it into one. And that combined knowledge helps the smaller subnets do their jobs even better.
It's like a whole brain trust of BERT models. This is just blowing my mind. It feels like we've only just started to explore what flexible BERT can do. Where do you see this research going in the future?
One really exciting possibility is integrating that early exit functionality directly into the gating modules. That would give it even more control. It could optimize the width and depth at the same time based on the text. And another cool idea is applying neural grafting to other models, not just BERT, maybe even different types of neural networks altogether.
The possibilities are endless. I can already picture a future where AI systems are not only super powerful, but also really efficient. We could run them on all sorts of devices, and they could tackle even more complex tasks. But with all this power, we have to think about the responsibility too, right? As we build these advanced systems, we need to make sure they're used ethically and that they benefit everyone.
Absolutely. We have to make fairness, transparency, and accountability top priorities as we keep pushing the boundaries of AI. These technologies should be used to empower people, not to create new problems or make existing ones worse.
Well said. This has been an amazing deep dive into flexible BERT. I bet our listeners are just as excited about this research as we are.
It's been a real pleasure discussing all this with you. I hope everyone listening has enjoyed learning about this as much as we have.
Me too. So until next time, keep those minds curious and keep exploring. Who knows what other incredible breakthroughs are waiting for us in the world of AI?
The future is bright, and it's definitely flexible.
So we've been geeking out about all the cool things flexible BERT can do, but how do we actually know it works? Like, how do they test this thing?
Well, they used a bunch of different benchmarks and metrics to really put it through its paces. For natural language understanding, they use GLUE. It tests things like sentiment analysis, question answering, and textual entailment.
So they threw a lot of different language tasks at it. What about reading comprehension? How do you test a model's ability to actually understand and pull out information from a text?
For that, they used SQUAD, the SQUAD dataset. It's a pretty common benchmark for that kind of thing, seeing if a model can answer questions based on a given passage of text. It's a tough one, because the model has to not just understand the words, but also figure out the connections between different parts of the text.
Right, so they were looking at a whole range of language skills. But beyond just getting the right answer, they also cared about efficiency, right? Like, how did they measure how much brain power flexible BERT was using?
Right. They used FLOPs for that. It stands for floating point operations. And it basically tells you how many computations the model needs to do for a specific task. Fewer flip-flops, more efficient model.
Ah, so it's like measuring how much mental energy the model is using. Less energy is better.
Exactly.
Right.
And they compared flexible BERT's flops to those of other BERT models, like the original one, BERT base, and then DistilBERT and TinyBERT, which are supposed to be really lightweight.
Did they also measure speed? Like how fast flexible BERT could process information?
Oh, yeah, for sure. Inference speed is super important, especially for things like chatbots or voice assistants where you need responses in real time. You don't want to be waiting around forever.
Absolutely. So they tested it on both CPUs and GPUs.
Yep. Wanted to see how it performed on different hardware.
So what was the verdict? Did flexible BERT actually live up to all the hype?
It really did. It was consistently beating those other efficient models, not just in efficiency, but in accuracy too. And get this, it even matched, sometimes even surpassed, the original BERT model in some cases. And all that while using less power.
That's amazing. So they really managed to get both efficiency and accuracy. Any specific examples that really stand out?
Yeah. On GLUE, they saw a 1.3-point improvement in the average score. And on SQUAD, they saw a whopping 2.2-point jump in the F1 score. And all that while using about 45% fewer computations than BERT base. Pretty impressive, right?
Those are huge improvements. This really feels like a turning point for natural language processing. It means we could potentially run these powerful models on things like phones, wearables, even those smart refrigerators we were joking about.
Exactly. And it's not just about putting AI in new places. Flexible BERT could totally change how we use AI right now, too. Faster translations, more accurate chatbots, even AI tools that help us understand and even write creative content.
It's mind-blowing. It feels like we're entering a whole new world of AI, one where these models are just seamlessly integrated into our lives.
I know. It's a really exciting time to be working in AI. And who knows what the future holds. I bet we'll see even more incredible applications as research keeps going.
I completely agree. This has been a fantastic deep dive into flexible BERT. It really is pushing the boundaries of AI, from the way it uses neural grafting to its dynamic inference framework.
It's been a pleasure exploring this with you, and I hope everyone listening has enjoyed learning about this research as much as we have.
I have no doubt about that.
Yeah.
So until next time, stay curious, keep exploring, and let's see what other amazing AI breakthroughs are out there.
To a bright and flexible future.